All right. So survival. If we look at the at survival analysis, so here, figure 2 on the left is an example of a survival curve. It's called relapse-free survival curves for a lung cancer trial. So with survival, you have a couple definitions that you need to understand. There's the what we call survival probability, and the survivor function, or at least the way it's represented, is by an S with the lowercase t italicized. So that represents that probability of that survival. And it's the probability that the individual survives from the time of origin to a specified time in the future. And it represents a cumulative non-occurrence rate. Then there's the median survival time. And we use the median because the mean, if we were to use the mean survival time, as we already mentioned, can be affected by censoring, or essentially what it would see as missing data. So you're going to have a big difference between a median and the mean. And median survival time is the time at which half the patients have suffered that event. And so that's an important outcome measure that you'll see a lot of times published in the literature. So what you see here, survival, say in this cancer trial, where there's a steep drop-off and then a leveling off. And each time somebody dies, each one of these represents, it's almost like a stepladder. What you can see in this figure, you can see little plus signs in there, which are when patients were censored, that maybe they were lost to follow-up, maybe they died from another cause, so on. But if we get down here, so with radiotherapy, it's showing you is that the median survival time was 0.64, and I believe this is in, well, this is not showing you, it's the probability over here, so it's 0 to 1, so that's the probability of survival. Here is time on this axis here. So the median survival was 0.64 years with radiotherapy. But when they compared that to radiotherapy plus SAP therapy, basically a platinum-based chemotherapy, that survival was almost double. 1.2 years. And so that represents the median survival time in each of these. And this is most likely a randomized controlled trial that was following these patients until, in this case, the event of occurrence was death. Now, there's some other terms you need to be familiar with. There's the hazard and the hazard ratio. And you can see here, hazard is represented by a lower h and the t for the time. And this is the risk of suffering an event at exact time t, which is called the hazard. And it can be understood as the instantaneous risk of death. Now, this risk may change over time, and so it is therefore dependent on time. So say, for example, if they consider time for administration of a medication to the occurrence of, post-op nausea vomiting, or the risk of nausea would be the hazard that would directly after the administration of the medication is higher than the risk of nausea, say 1 day or 1 week later. The one you're going to see most commonly reported in literature, and one of the YouTube videos does a very good job of explaining these, is hazard ratios. So when you're comparing two groups, you have the hazard function in group 1 and a hazard function in group 2. And you essentially you get the ratio of those two. You take it the hazard rate in group 2 divided by group 1, as you can see here, and you can come up with a hazard ratio. So the hazard ratio is a measure of how high the risk of an event, in this case instantaneous death or instantaneous risk of whatever event you're looking at, in comparison to group 1. So group 1 is always considered the reference group. And it shows you here. So a hazard ratio, if it's greater than 1, that means the risk of an event, say nausea, is higher in group 2 than group 1. If it's less than 1, the risk is lower. And if it's approximately 1, or if the 95% confidence interval includes 1, the risk of the event is equal in both groups. Here's just another way of looking at that. So what we just said is that in time to event analysis, the hazard function is defined as simply the instantaneous event rate, or that probability rate. And you can see what I have right here. Greater than 1, the event is greater in group 2 compared to group 1. Less than 1, group 2 is lower than group 1. If it includes, if the 95% confidence interval includes 1, just like all the other confidence intervals we talked about, with like odds ratio and relative risk, then the finding is not statistically significant. So sometimes when you're reading an article, you may see that they're not including the p-values, but rather they're including the measure of precision with that confidence interval. So here's an example. So if you have a hazard ratio of 2.3, so this means that the risk of death in patients with, say, metastasis is 2.3 times higher than those without metastasis. Or it's 130% higher. And the way they calculate that is, a hazard ratio, it's 1, either it's above or below 1. So what you do is you subtract 1 from the hazard ratio, and that'll and you convert that to a proportion, and that's how you can say, and essentially, it's like an effect size. Now, we use what's called Kaplan-Meier curves to help graphically display and describe survival and survival times. We also can use these to calculate survival rates. And what it does is it calculates the conditional probability of the chance of surviving a time interval, or what's referred to as cumulative survival. And you can see here, this is an example from the study we did with some students several years ago, where we used a hazard ratio to model the time to complete motor recovery in a randomized controlled trial, where we had patients either receive they had a very dilute local anesthetic fentanyl epidural for labor, for vaginal delivery. And they were randomized either to a 30 cc saline bolus or a control group. And we measured the time to complete motor recovery after the bolus. And then we used survival analysis. And what this shows us here is that the hazard ratio was 1.3, but it was not statistically significant. The reason I can say that, even though the p-value is not there, is because that confidence interval includes 1. All right, here's some examples from your readings that shows you how they go about calculating the survival function. So we have here survival times and what they call Kaplan-Meier estimates. We have the patient number here. Did they die or not? Yes or no. How long did they survive? How long till that event? And this is the number of patients at the beginning. So there's 5, 4, 3, 2, 1 to the end of the study. D little I is number of patients who have suffered the event at that time. So what they show here is at month 4, 1 of 5 patient dies. So the probability of surviving until at least the end of that month is, month 4 is 4/5, so is 80%. So that's where they get right here. Then we go to month 7. Another patient dies. So the probability of surviving it until at least the end of the month 7 is, you take 4/5 times 3/4. So probability of survival is 60%. So overall survivability at 7 months is 60%. We go to month 9. 1 patient was censored. The patient did not suffer an event during the trial. So now there's only 2 patients remaining at risk. So the probability is still at 60% at this point. Month 10 comes along. another patient dies of cancer. So the probability there would be you take 4/5 times 3/4 times 1/2, which is 30%. And in month 13, they had one patient censored, so the probability of survival was 30%. So with each death, what happens, the Kaplan-Meier curve drops. You can see this, how it drops down with first patient dying. He's going, another one dies. Here you have a patient who is censored. And we keep going on like that till we get to our 30% survival at approximately 13 months with 2 patients who were censored. So that's essentially what a survival analysis is doing.